Here's a problem from the homework, section 1.4. Here, the question is solve for the matrix A if you're given that the inverse of an expression is equal to something. You want to be able to solve for A. So what we're going to do is I'm going to write this down. This identity plus 3 times some matrix A, the inverse of that is equal to some matrix 6, 1, 26, and 6 for this example. So we know then that this implies that I plus 3 times A is equal to the inverse of the right side. You follow me on that? Okay, Daniel? Okay, so now what we want to do is of that 2 by 2 matrix, let's find its inverse, and we set that equal to the identity plus 3 times A. So this matrix we find its inverse. So this becomes 36, that multiplier, 1 over AD minus CB, AD minus CB. So it's 1 over 6 times 6, 36 minus the 26 times 1, 26. And this is times, we're going to interchange 6 and 6, where it's the same thing, negate the 1 and the 26. So this is 6 here, negative 1, negative 26, and 6. Well, we're going to multiply each term by a factor of 1 over 10 on the inside. So this is 1 over 10, so this is 6 divided by 10, negative 1 over 10, negative 26 over 10, 6 over 10. Simplify him, and so this gives us, thinking about the denominator, 3/5, negative 1 over 10, negative 13 over 5, and then 3/5. So this is said to equal to the identity plus 3 times A is equal to this matrix here, 3 over 5, negative 1 over 10, negative 13/5, and 3/5. Right? So the identity matrix for a 2 by 2 is 1, 0, 0, 1, plus here 3 times some matrix A is equal to the 3/5, negative 1 over 10, negative 13 over 5, 3/5. So we're going to subtract both sides by the identity, so that gives us 3 times A is equal to the 3/5 minus 1 over 10, negative 13 over 5, 3 over 5. This is minus the identity matrix. So this is 3/5 minus 5 over 5, so we get negative 2/5. This is still negative 1 over 10. This is still negative 13 over 5. And this is 3/5 minus 1. That gives us again negative 2/5. So now divide each term in this matrix by 3, and we get the matrix A. Right? So this here implies that A is equal to 1/3 times that matrix, negative 2/5, negative 1/10, negative 13/5, negative 2/5. So that gives us negative 2/15, negative 1/30, negative 13/15, negative 2/15. And that's the matrix A. So basically, if you think about it, that problem it begs you to just go back and just rework, you know. You're given this outer layer of an onion, just unwind that onion. Yep. Any other questions? That's good, Daniel. Thank you. And your question was good too, my friend, about the proof, but just go back and watch that video. There's a lot of stuff in there, man. Of which that problem will be on the test, by the way. So, any other questions? Oh, the Lord bless you all, my friends. Any other questions? Okay. Let's review over. Here's what we're going to do today. 3 things. I'm going to go over the sample exam, work over some of those problems. Some of them that I've done before, I just refer you back to our notes or to the videos online. Secondly, I'm going to just talk about the test, just give you the breakdown of the problem and how the flow chart of those test problems will be presented to you on Monday. And then thirdly, I'm going to let you all talk to me. And we're going to all go online. You're going to go online. And we're going to look at the sample exam that's in Wiley Plus. And so we'll give you all, hopefully about 20 minutes, the last 20 minutes, if we can have that time set aside for you all to work some problems as well, okay? So I do a little bit, you do a little bit, and that all equals a whole. And is it Patricia? Okay. Say it again. Batisia. Okay. We missed you on Monday. Okay. Well, let's see. This is the sample exam. Number 1, multiplying matrices. The answer is there, so it's no fun anymore. We got the answer, right? So let's look at number 2. Yes, ma'am. You know, I think that was the one going back even to the, I think I copied that one out of the section, and I think over there, I think I told you all that first one's supposed to be a 9. Yeah, so it's the row times the column, so that's 6 minus 5, that's 1, plus 8, that's 9. Yep. I don't know if you recall, but when we were covering that section, I asked you all to do it in class. And I had kind of set it up where I had an error right there so you all could see that first one was 9. Everything else in there was correct. So very good. Is my pen working? Good. Yep. Perfect. Let's look at number 2. Use Gauss-Jordan elimination to solve the system. So we're going to take this system, write it as a matrix, and then just reduce. Okay? Use the 1 at A11. We have a leading 1 there, so that's good. So we use that 1 to get zeros below it. So here we'll say negative 4 times row 1 plus row 2, and then negative 2 times row 1 plus row 3. And so that gives us, just rewrite the first row. So this is a 0, it's a 0 there. So negative 4 times negative 2 is 8 plus 1. You get 9. Negative 12 minus 1 is negative 13. Negative 44 and 4 is negative 40. Negative 2 times row 1 plus row 3. So the first one's 0. You get 4 minus 1. You get 3. Negative 6 plus 3. Negative 6 plus 3 is negative 3. And then negative 22 plus 10 is negative 12. The next goal is where that 9 is to get a 1, and then use that 1 to get zeros above and below. Notice that 9 and 3 are multiples of each other. Let's use the 3's and the 9's to our advantage. So I'm going to take this 3 and get a 0 here, and then interchange after that rows 2 and 3. And then we just divide this row by 3, and that'll give us a leading one up there. So here, what I will do is say negative 3 times row 3 plus row 2. It gives us a new row 2. Rewrite everything else. Is anybody from Decatur? Yeah. So did they really close down McCullough Seafood in Decatur? Yeah. They had the best frog legs in town. You know, has anybody had the frog legs before, or just frog legs period? We used to, the class and I used to go over there at least once a semester and try out the frog legs, but sorry, Charlie. Okay. So here, multiply negative 3 to row 3, add that to row 2, so this becomes a 9 minus 13, so we get negative 4, and then 36 minus 40, negative 4. So can you all handle this? I'm going to interchange rows 2 and 3, and then while I'm doing that, I'm going to divide that second row by negative 4 and divide that third row by a 3. Can we do that at one time? Okay, so you kind of see that. So interchange rows 2, row 3, and then we'll do our division. And while we do that, so 1, negative 2, 3, 11. It's going to be a 0, 1, negative 1, negative 4. This is 0, 0, 1, and 1. And so after we did the swapping, 1/3 times row 2, then negative 1/4 times row 3. Now after that, let's use this one to get a 0 where that negative 2 is. Yes, sir. That's Gaussian elimination. Right. So here, Gauss-Jordan, go all the way. Right? Gauss-Jordan, get 1s along the diagonal, 0s everywhere else. Yep. Gaussian elimination, you want to get 1s along the diagonal, 0s below that. And then you go back and back substitute. Personally, like I said in class, I'll say it again, personally, if the question says to use Gaussian elimination, for me, always just still do Gauss-Jordan for all of them. Because that's the one. You go all the way, you solve the whole matrix completely, right there in the matrix, you get your answer, you're done. Right? So we'll say 2 times row 2 plus row 1. Going to rewrite rows 2 and 3. So 1, 0 there. 2 times this negative 1 is 2 negative 2 plus 3, which gives us a 1. And then 2 times the negative 4 is negative 8. And so 11 minus 8 is 3. And so now we use that 1 at A33 to get zeros above it. So we'll say simply negative times row 3 plus row 1, and then just add row 3 to row 2, and you get what you want. Now when we do that, that coefficient matrix is the identity, and we do the work over here. So row 3 stays the same. So we said negative row 3 plus row 1, so it says negative 1 plus 3 just gives us a 2. And then you add row 3 to row 2. 1 minus 4 is negative 3. And that's what the answer called for. And we're good. Any questions there? Very straightforward, but here's the thing. You know, when you're doing those steps, just one simple error just throws off everything after that. So just be very careful. How do you know if you got the right answer? Well, for each equation, you're going to plug in x sub 1 for 2, x sub 3, x sub 2 for negative 3, and x sub 1, x sub 3 for 1, these numbers. Yeah. So you check here, 2 minus 2 times negative 3 plus 3. Well, that gives us 2 and 3 is 5 plus 6, that's 11. Good. Now, I tell you what, our enemy is busy. If you just check that first row and think that everything is fine, I've seen it where the 3 numbers can work out perfectly for that first equation, but they could be wrong in like the second or third equation, and your numbers are wrong. So we're going to check all 3. This is 4 times 2 for that second equation, plus x sub 2 is negative 3, and then minus 1. So we get 8 minus 4, we get 4. That's good. Then the last one, 2 times 2 minus a negative 3 plus 3 times 1. So we get 4 and 3 is 7 plus 3, we get 10. So you're good. So by all means, you know, I think this is one of the classes that you'll take, and while you're working the problem, you can go back yourself and check to make sure you got the right answer, and you'll know before you even leave the test if you're right or wrong. You know, when I was in history class and you write that essay or you answer that question, you don't know if you're right or wrong until you go back after the test and look at the book, and then you say, dang, you know. Anybody feel me? Anybody been there? So, well, number 3, use Gaussian elimination to solve the system. Like I said, I'm going to go ahead and just use Gauss-Jordan on this guy and just work it all the way. Now, unlike the sample exam on your test, you won't have the answer sitting right there. Dang! That'll be pretty good, right? I've thought about that. But then here was the problem with that. If I did that, then the problem is really hard, you know? And it's like you probably wouldn't even get the answer unless somewhere in there you just lied and said, okay, here's the answer right here. And none of your steps make sense to how you got that answer, you know? So I wouldn't do you like that. Okay. So try to give easy problems on the test, man. You know, bless your hearts, you know, folk who take, you know, some of those online tests, because the computer is generating some of those problems, and some of those answers can be very wacky. You know, but when you're in class like in here and I have to actually grade it, I want the numbers to kind of work out to be smooth, because I have to grade it, and I like to grade easy stuff because I'm just simple. Okay, shh, 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 shh. 3, 2, negative 1, 6, negative 5, 16, negative 6, 4, 14, 9, 6, negative 3. All right. Well, it looks like since the first equation, the first row has a common factor of 3, let's just divide or multiply everything in row 1 by a 1/3. So we use the A11 to get a 0 where the 2 is, and then use A11 to get a 0 where that negative 1 is. So negative 2 times row 1 plus row 2, then row 1 plus row 3. Yes, sir? Row 1. Thank you. Bless you, Michael. Man, I got this. Does anybody know where my office is? Does anybody, Michael? Let's see here. Let's see here. Well, what's your first name? Michael. Two Michaels, and both Michaels know where my office is. That's good. Michael, can you run upstairs? Just let my secretary know that I want you to go and get something off my desk. On my desk, there's this sticker that says like I love math or something like that. It has like the square root of -1, and I think it's a big one too, and it says like Hawks Learning. If you can get that for me, okay, appreciate it. Said that I would give that away to somebody who either gets something right or puts me on the straight and narrow. Which I'll be passing that out all day, every day, My wife, I tell you, my mama tries to correct me. I said, Mama, I'm a grown man. I don't tell her that, though. You think I'm crazy, man. There's one thing you don't mess with. You don't mess with a black mama, I'll tell you, man. She'll straighten you out pretty good. What you say? Mama, I'm grown. She gonna come to my house one time and we're gonna try to point some stuff. Mama, this is my house, Mama. You go home to your own house, Mama. You know, I ain't tell her that. I was thinking about it. You think I'm crazy. Anyway, okay. Thank you, Michael. So we're going to rewrite row 1. -2 times row 1 plus row 2. So it's 0 there. We get -4, -5, -9. We get 4 plus 4 gives us an 8. -6 plus 6 is 0. Just add rows 1 to 3. Right. So now, notice here rows 2 and 3 are just factors of each other. Well, that's good for us because remember we talked about anytime you have two rows that are the same or they're multiple, scalar multiples of each other, then you know the outcome is that you will have infinitely many solutions, right? Because you can cancel out an entire row. So notice that if we say -2 or just 2 times row 2 plus row 3. Thank you, Michael. And see, Michael McKelvey, I wouldn't work you because you got it straight. So we worked the other Michael. Yeah, put that on. I wore it yesterday all day long. I wore it around campus. That's your pen for today, and bless your heart. Yeah, either that or on Monday when you come back, and then we'll just keep passing it around, okay? All right, and if you mess up today, we have to take it from you and give it to somebody else, you know. But I had it on all day yesterday, man. I have another pen that says something about, I think I wore it here one day, that we used to do it like this, or this is how we used to do it, and I got a big X mark through that. People say, we've never done it like that before, and I got an X on that. I had that at church a few years ago, and folk looked at me kind of funny. Okay, anyway, so 2 times row 2 plus row 3. So that leaves row 3 with just all zeros. Now, in terms of Gaussian elimination, that's it. What I'm going to do is that we can actually continue. Gaussian elimination is that, but you still have to solve. If there's infinitely many solutions, you have to tell us what those infinite solutions are. Give us that infinite set. You can stop there, but you still got to simplify using algebra, or you can just keep it here and just do the algebra on the matrix. So here, this implies infinitely many solutions. We must find the infinite set. So take this matrix, and you know that the idea is to get a leading 1 at A22. Just divide everything by row 2 by -9. So we say -1/9. The idea is that you're not actually dividing, but you are. You're just multiplying the matrix by a scalar. And the scalar happens to be a fraction, and so obviously we are dividing. That question comes up, and I come back and ask you that even on the test, and we'll see how you respond. Then we use the 1 at A22 to get a 0 above it, and after that we can't do anything else, because anytime you're trying to get the matrix reduced to Gauss-Jordan, you want to get the main goal first. When you come to each column, is to get a 1 at the leading 1 position on the diagonal, and then zeros elsewhere within that column. When you come to column 3, there is no leading 1 here at A33, and you can't get a leading 1 there. Thus, you cannot simplify the values above it. So once we deal with this leading 1 at A22 and get a 0 below it and above it, then after that, you're done. Okay. Yes, sir. Okay. Here, if you have all zeros, you have infinitely many solutions. Then we say we must find the infinite set, right? In terms of, you have zeros all on the bottom row, but I have a leading 1 at A22. So that means that I can still get a 0 above it and below it. But when I come to A33, this position, there's a 0. I cannot take this 0 to cancel out -2. I cannot take this 0 to cancel out -8/9. I got to have a leading 1 there. Since I don't have a leading 1 there, then once you simplify column 2 with the zeros and the 1, then you're done after that. You should be able to, from that matrix, look at it and tell what the solution, the infinite many solution set will be. Okay, let me show you. So what I'm doing is how you're going to do it. So what we're going to do is say -2 times row 2 plus row 1. So that last row is still 0. Put in the second row. is a 1, 0. So we say negative 2 times 8 over 9. So that's 16 over 9 minus this 2. So we get 16 minus 18 over 9. So it gives us negative 2 over 9. And then negative 2 times 0, 0, plus 3 is just 3. Now look, now say for example, if you didn't have the answer over here, then you couldn't see this. But I want you to see how from this matrix, you see how the answer works itself out. Remember, this 1 represents 1 times x sub 1. This is x sub 1 is equal to 3. That's the 3 there, right? Get this term on the side with the 3, that becomes plus 2 over 9 times t. T is the floating parameter from x sub 3. Since x sub 3 is there, but it's been canceled out by a coefficient that's 0. It's really 0 times x sub 3. So x sub 3 is not 0, it's the coefficient multiplied to it. X sub 3 still exists. What is it? It can be anything, right? And then look at this next term for x sub 2 is 8 over 9t. This is x sub 2 is equal to 0 plus 8 over 9t. Now, just if you didn't get that, it's okay. Let's just rewrite this matrix as a system. This is x sub 1 minus 2 over 9. X sub 3 is equal to 3. Then the next equation is x sub 2 minus 8 over 9. X sub 3 is equal to 0. That's all we got. Notice how both equations have an x sub 3 in them. So both equations depend on x sub 3. So the dependent variable here, or the floating variable, would be x sub 3. Scroll down a little bit. We don't need this. This was our scratch work. If you look at the main diagonal, do we have a different color? On the main diagonal where we have 0, that position represents the floating parameter. So x sub 3 is the floating parameter. What does that mean? That means that x sub 3 can be anything. So here we say let x sub 3 equal to t. T is any real number. So we have now x sub 1 minus 2 over 9 t is equal to 3. X sub 2 minus 8 over 9t is equal to 0. So this gives us x sub 1 is equal to 3 plus 2 over 9t. X sub 2 is equal to 8 over 9t. And x sub 3 is equal to t. Right? So your solution set is that. X sub 1 is 3 plus 2 over 9t. X sub 2 is 8 over 9t. And then x sub 3 is t. That's the solution that you have to give me. So Daniel, thank you for asking the question, because the question was, if I have all zeros in a row, do I stop? No, you want to keep on working. You want to give me the infinite solution set. And that's a good question, because I remember when I was teaching Math 112, and apparently I probably made a statement like that, but I still worked the problem out all the way completely, and there were 2 or 3 people who gave on their test they reduced the matrix down. They had a row of all zeros, and they just said infinitely many solutions, but they didn't tell me exactly what those solutions were. So here you have to tell me what they are. Right? X sub 1 is what? X sub 2 is what? X sub 3 is what? So thank you, sir. Next. Find all solutions to the homogeneous system. Why here for this problem? My question is, why are the answers for x sub 1, x sub 2, x sub 3 all 0? It's homogeneous, but sometimes you can have a homogeneous system and the solutions are not all 0. It's squared. That's the key, right? The system has the same number of rows as it has the same number of columns, right? Or the same number of equations as the same number of variables. I have 3 variables, 3 equations. It's homogeneous. Automatically, by that theorem, the solution is the trivial solution. Okay? So no work there. Very good. Find the inverse of the given matrix and check matrix multiplication. You recall if it's a 2 by 2, you use that formula, right? So, what in the world? Is that corrected? I tell you, man, these computers, funniest thing in the world. I just want to erase. I think what's happening, this is an old document. Let's call this A. And so A inverse equals to 1 over 2 times 2, which is 4, minus 3 times 1, which is 3, times, we invert, we transpose the diagonal positions where they're the same there, and negate the opposite terms, so negative 1, negative 3, and 2. And so just very straightforward. Well, this matrix is being multiplied by the factor of 1, so all right. I will have a question, just like 5 and 6. So there'll be, can you get the inverse for a 2 by 2? Very straightforward. Can you get the inverse for a 3 by 3? And yesterday, that's what we worked on. So let's look at this problem here. We said that you start with the matrix on the left side and the identity on the right side, and then you reduce until such that on the left side you have the identity matrix, and on the right side you have A inverse. Now, if you cannot produce the identity matrix on the left side, A inverse does not exist. Okay? And that's what happens with this problem right here. Let's see. Do you all get excited and loud when you're watching a football game? Or are you like this when you're watching a football game? Well, I guess you say this is not football. So, but I've been around some folk when I've seen them at a football game, and I've seen them at church, and they act about the same. They're quiet at church, and they're quiet at the football game. So when I saw him at the football game, I couldn't complain about him at church anymore. I said, okay, brother, you're just a quiet soul. Bless your heart. Okay. Okay. This is a lively bunch, I tell you. Okay. So we're going do the same operations. Take the matrix. We want to perform Gauss-Jordan on the left side and do the same thing to the right side over here to that identity matrix. So first we're going to use the 1 to get a 0 where the 2 is. So negative 2 times row 1 plus row 2. Zero there. 6 minus 5 is 1. Negative 8 plus 7. Negative 1. Negative 2, 1, 0. I already have a 0 there at A31, so nothing to do for row 3. Now we'll take this leading 1 at A22, excuse me, and get zeros below and above. Something interesting happens when we do that. So let's say here, row 2 plus row 3. And once we do that, we say as well, 3 times row 2 plus row 1. But once you do that first operation, we're going to get something good. So I'm not going to even do that. Since I'm not doing that, I'm not going to write it. This is 0, 0, 0, negative 2, 1, and 1. You see those zeros right there, that third row, all zeros? You stop. Because here where that 0 is at A33, that can never be a 1. And so we cannot produce the identity. The left side will not produce the identity. So because of that, the inverse does not exist. Didn't say it was A, so. Because the left side matrix cannot produce the identity matrix. Okay. Find all values of A and B for which the matrices A and B are both not invertible. Yes, sir. Going back to 6. Okay. You can, yes. You will. That's right. Yep. You can interchange the rows. That's fine. Yep. But even if you interchange the rows, you're still going to have a row of all zeros over there on the left side. So it still will not be invertible for this particular problem, right? Yeah. But can you interchange rows when you're trying to find the inverse? Yes, you can. You remember there were 3 basic elementary row operations. The first one, you can interchange rows. That applies to find the inverse too. You can multiply a row by a non-zero number. And thirdly, you can add a multiple of one row to another. You apply those even to finding the inverse. Yes, ma'am. Number 7, find all values of little a and b such that matrices A and B are not invertible. This problem begs for some knowledge that you know of concerning these matrices to be able to solve. It begs for some knowledge. Let me ask you, do you know what that is? And I just want to throw this out and show you how important this is. I forget the exact chapter in Genesis, but there's like 1 or 2 chapters in Genesis where it says that Isaac and his family, they go out and they dig up the wells of his father Abraham. When they dig those wells up, then there's some people in the land, they come up and protest against Isaac and say, no, you can't do that. We live here now. And so Isaac says, okay. He moves somewhere else. He digs another well. He gets over there and he has his cattle and his men working, and some people in that land come up and say, hey, we got rights here to this property, to this land. You can't do this. And so Isaac says, okay. He moves again. He digs a well. Have you all read that in Genesis before? Go ahead, that's homework. Go read that. Okay. And face value, you don't think nothing of it. I didn't think nothing of it when I first read it. Okay, he goes and matter of fact, I heard a preacher preach a sermon. Dig another well. You know, we all got happy. Dig another well, yes. You know, and he had well symbolized in something, life, whatever, continuation of life. Good message. But there was something about that story you needed to know to actually understand what was going on. Do you know what was behind that story? That I didn't even know until I kept on digging. What's behind that story was that Isaac, and we heard about Abraham, Isaac, Jacob, right? Isaac, right? Isaac was not like his daddy Abraham. You know, Abraham was a fighter. I mean, he got down with those 5 kings of the plains, and he slaughtered them, man. He had his 300 men, his soldiers, and look, they saying we can't graze on this land. And Abraham said, who? I mean, Abraham, Abraham's something, dude. He didn't play. You know what I'm saying? I mean, he was a fighter. You all listen to me. Isaac wasn't like that. Isaac was timid. Isaac was shy. So when the people of that land came up against Isaac and said, we were here before you. But Isaac was like, no, my daddy dug this well. And they said, but when he died, he left. And we came here. And so Isaac said, okay, you got to worry about it. I'll move on. Now, if it was Abraham, it would have been a fight. You see that? I mean, it was so bad. You remember in the story when Isaac and Rebekah's son, Jacob, he goes and he lives with her family, Laban, and he goes over there and then he ends up marrying Rachel and Leah. You remember that story? Right? But here's what's behind it. What's behind it was this. Rebekah was like to her husband, Isaac, she was like, I don't want my son growing up like you. Because you're shy and timid. How come you can't be like your daddy Abraham? So I want my son to go live with my brother and my cousins Laban and them. So he can have the idea of a real man, a real father. Wow. See, that's what's behind the story that you don't get. There's something behind this problem. And if you don't know what's behind the problem, you don't get the problem. You see what I'm trying to get at? Right? It's like some real stuff behind it. Here's what's happening. We call these matrices a diagonal matrix. A diagonal matrix is any matrix with entries along the main diagonal and zeros elsewhere. I have entries along the main diagonal, I have zeros elsewhere. See that for matrix A, for matrix B, I have a 5 and a 2A minus 3B minus 7 on the main diagonal, I have zeros elsewhere, right? It's a diagonal matrix. Here's a theory. The theorem says that any diagonal square matrix is invertible if the entries along the main diagonal are all non-zero. That's what's behind it. If you know that, you can solve the problem. Let me write that down. Note, matrices A and B are called diagonal matrices. Diagonal matrices are said to be invertible or have an inverse if each entry along the main diagonal are all non-zero. So with that in mind, let's go back and look at the question. Find all values of little a and little b for which a and capital A and B are both non-invertible. So what they're saying is you can't make the 3 0, you can't make the 5 0, but you can set a plus b minus 1 not equal to 0, and you can set 2a minus 3b minus 7 not equal to 0. Solve for a and b, and then we say if a and b are these numbers, then the matrix is said to be invertible or not invertible. So let's see. So we set a plus b minus 1. Well, it says that are both non-invertible, so we're going to set them equal to 0. Yep. And 2a minus 3b minus 7 equal to 0. If you set them equal to 0, that means that the sum, a plus b minus 1 equal to 0. If I have a 0 on the main diagonal, if it's a diagonal matrix, then that matrix is not invertible. And so we set 2a minus 3b minus 7 equal to 0 as well. And if we solve for little a and b, find those numbers. If little a and b are those numbers, then the matrices are not invertible. So this implies that a plus b is equal to 1. 2a minus 3b is equal to 7. Now that's just a simple system that can be solved, right? So 1, 2, 1, negative 3, 1, and 7. And when you're finished, you end up with a is equal to 2 and b is equal to negative 1. Any questions there? Number 8, we did that one already, right? We did that one already. Number 9, I don't know if we did that one or not. Did we do that one? You remember that one? Let A and B be square matrices such that A times B is equal to 0. Show that if A is invertible, then B is equal to 0. Is that straightforward? Do you see that one? It says that you're given A times B equal to 0, and then it says assume that A inverse exists, right? If A is invertible, then can you show that B is equal to 0? Right? Can you get that one, you think? Given A times B equal to 0. If A is invertible, that is, A inverse exists, then A inverse times AB is equal to A inverse times the 0 matrix. We associate A inverse times A times B. Well, the 0 matrix times anything is 0. A inverse times A is the identity, times B is equal to 0. Just multiply both sides by A inverse, and it was left multiplication. Right multiplication of A inverse won't work. We use left multiplication of A inverse to both sides of AB equal to 0. Right multiplication of A inverse will not work. Here's a question for the textbook that I'm writing. Why? That's good. Oh, you got to know it. Okay, number 10. Find values of A, B, and C so that the graph of the polynomial ax squared plus bx plus c passes through the point -1, 0 and has a horizontal tangent at 2, -9. Do you understand the problem? You understand the problem? Can you see or depict the graph of the problem? That's important. So when I was at home, Mama always said when she asked me a question, she expected for me to say something. Yeah, that's how it was at home, right? Was your mama like that too? Because if you ain't saying nothing, it was, hey, something's going to happen. So my question again, do you understand the problem? Can you depict or see the graph? Ideally, maybe not exactly, but just got to have some idea. Sir?
Sure.
I don't know how to respond to that. No, I don't know. Whether it's mathematics, mathematical science, physics, chemistry, engineering, whatever problem you're given, whatever problem, no matter how complex it is, you got to make sure that within that problem, you understand what we're trying to get at. Doesn't mean you know how to solve it. I'm not saying that, okay? But you got to have an idea of what the problem is asking. Can I see it? And then if you can see it, you can use the mathematics to build what you want to be able to get the solution. So we got these values A, B, and C. We have this parabola, right? And we know that there's a point that goes through the parabola, some point x sub 1 comma y sub 1 that goes through the parabola, right? Some value x, some value y. And then it has a horizontal tangent here at the point 2 comma -9, which means that the graph also goes through 2 comma -9, but at that point of the graph, there's a derivative. And the derivative, if it's horizontal, the derivative is equal to what? 0. Who said that? Ali, thank you. I got to get another pen for. Are you sure, Michael? Okay. Hey, we're passing this. I love math, man. Oh, it's feeling so good, guys. Okay. Do you understand that if the derivative is 0, that's synonymous for saying you have a horizontal tangent? That's what that means. All right? So, so here's the idea. And this is not drawn to scale, but just to give you an idea what's happening. Let's go down a long way. All right. So I got 1 point at -1, 0. I know that I have another point at 2 comma -9. 2 comma -9. if it's a horizontal tangent, that means that that's also my relative minimum. Horizontal tangent, right? In other words, p prime of x is equal to 0 there, right? The derivative is set to equal to 0. It's not good, friends, if you take these classes and we don't just understand in English what the terminology means. You know, the book says wisdom is the principal thing, therefore get wisdom. But with all thy getting, get an understanding, because if you don't understand it, go out and pick corn. Pick sweet potatoes. That's what I did when I came up. Because I got more enjoyment out of that. Because my grandfather, who had the farm, he couldn't read or write, but he knew all about farming. He'd tell us, why y'all going to school and you learn all this stuff and you don't have any common sense, because we couldn't do the stuff that he would ask us to do out on the field. Make sure you understand it. And if you don't understand it, ask the questions until you get to understand it. Okay, anyway, let's see. So the first point is -1, 0. So we have p of -1 is equal to, look at ax squared plus bx plus c. I'm going to plug in, replace the x with -1. So here I get a minus b plus c. That's equal to 0 according to this, right? X is -1, y is 0, right? This is y. Then the next point is p of 2. So wherever I have x, I put 2, so I get 4a plus 2b plus c. That's said to equal to -9. You see, the tangent is a point on the graph, and it's also a point on the tangent. That means it's also a point on the derivative as well, right? Why is the computer slowing up on me? Okay, good. So the next thing you have to do is find, I think it's easy, to find p prime of x. This is 2ax plus b. Here it says it's horizontal, which means that the derivative is equal to 0. The point x, I know, it says that and has a horizontal tangent at x equal to 2. So this is p prime of 2. Look at the derivative. This is 2 times 2. I get 4a plus b. That's equal to 0. I have a 3-by-3 system. The 3-by-3 system, this crazy computer, I tell you, acts like the old dog we used to have when I was growing up. The old dog was named Moochie. Moochie was crazy. Moochie, get your butt out the house. The dog wasn't supposed to be in the house down in the country. You know, we had a screen door. He had to get through that. He'd tear up that screen door to get in the house. Man, my grandmama have a fit. Moochie, get your butt out to his house. Anyway, okay, look. You got the matrix, 1, 4, 4. Y'all don't like me today. We used to be friends. This is 1, 1, 0. Something happened. I don't know. Right? Take that matrix, solve, reduce it. You get the answers that we have here. Okay. You're solving for little a, right? Little b, little c. Okay. Number 11. Let me cover 11. And you got the monster theorem. You got that online. And then we'll go over the true and false questions. I'll make some statements about that. And then I try to cover the test review. And then lastly was for you all to go and do the sample exam in Wiley Plus. But since my time is of essence, I won't be able to get to that. You just do that, when you get home or on your job and it's boring, right? You can do some math. No. Anyway, assuming the state of inverses exists, prove this guy. There's a problem like this somewhere in Wiley Plus as well. Huh? Yeah, that's a good section. Don't you love this class? Okay, no comments. Anyway, they really start talking there. They're like, well, okay. So assuming the inverses exist, which means that if you have a matrix given, they're saying the inverse of it also exists, even if it's a quantity. So if you have C plus D times D transpose, the inverse of that, then they're saying that its inverse exists, which is C plus D transpose. So the inverse of the inverse is the original matrix or the original expression. So we want to prove that the left side equal to the right side. So what you're going to do is I'm going to multiply left multiplication of its inverse to the left side on this side and the left side over here. And then I'm going to take this expression and multiply right multiplication of its inverse to this side and also over to the left side. You get that? And once you do that, simplify it. Well, how do we learn? I think we learn by seeing, we learn by hearing, and you learn by smelling too, sensing. But then you also learn by writing. So if I say it, you don't get it, let me write it down, then maybe you'll get it when I write it down, okay? So I'm going to, let me just write it and then I'll make some comments about it. So here the left side is C plus D times D transpose times C plus D transpose inverse D. Now watch this. This is times on the right side, right multiplication of the identity plus D transpose C inverse D. That's the left side is equal to left multiplication of C plus D transpose times C inverse D times I plus D transpose C inverse D inverse times I plus D transpose C inverse times D. Let me write some comments here so you can see. So you can see what I see. All right. This guy right here is left multiplication. Here it is right here. Left multiplication. This term right here is right multiplication. Okay. Do you see that now? I took the regular equation. I got something on the left side equal to something on the right side. Right? So this is what we started off with. This is right here on the left side. It's on the right side, right? So I did left multiplication of its inverse to both sides. Now I looked at this guy, and look, to simplify it, you got to multiply something on his right side. Because if I multiply over here with the C inverse D to try to cancel this guy out, I can't do it because whatever I multiply right here to the C inverse D has to be multiplied by C inverse. Because matrices don't step over other matrices, right? They deal with the guy that's right there by it. You know? So if we're gathering, it's the philosophy of just common courtesy. If we're in a room, I'm talking to you. If this guy back there is yelling at me, hey, man, come on, that's, mama call that's just ignorant, We talking. He's back there, hey, look. I'm going to get back there. When I do, we'll talk, That's what matrices are doing. Matrices, the one next to it, it deals with the operation, right? It doesn't jump over. Numbers can do that, right? You can say 2 times 6 times 7 is the same thing as 2 times 7, times 6. You can commute like that with the numbers, and that's fine. But matrices are more sensitive. So now, where does the time go? So look, so it's this matrix times its inverse just gives me the identity matrix, and that's times that D sitting there, right? And then here I have the identity plus D transpose C inverse D. That's equal to, now this term over here times this inverse just gives me the identity there. So this leaves me with C plus D transpose times C inverse times D times I. So here, the left side, now I times D is just D, so it's multiply D times parentheses. I get D plus D times D transpose C inverse D. I'm finished on that side. Equal to, this becomes right multiplication of C inverse times D. So it's times C times that, so this is C times C inverse times D plus D transpose times C inverse times D. Now notice here that you can simplify this because C times C inverse is just the identity times D. That's just D plus D transpose C inverse D. Let's go back and put the left side. This is D plus D times D transpose C inverse times D. Is the left side equal to the right side? Is the left side equal to the right side? Yeah, we're done. Number 12, understand and be able to apply the definitions for equal matrices, multiplication of matrices, transpose, and the trace of a matrix. We covered that. Go back and review that online. Be able to prove the monster theorem. We proved that also online. The true and false, important. Here's the kicker about the true and false. I'm going to give you true and false questions. If it's true, you just say true. If it's false, you have to tell me why it's false or justify either with an example or with a theorem or property. What the devil is a liar. I'll tell you, man, I just can't stand these computers. But anyway, oh boy, here it goes again. 2 n by n matrices, A and B, are inverses of one another if and only if A times B is equal to B times A equal to 0. I'm giving the answer is false. Why is it false? Exactly. Because it's not because. Because A times B equals to B times A is equal to the identity, not the 0 matrix. You see that? That's why it's false, right? If A and B are invertible matrices of the same size, then AB is invertible, and the inverse of A times B is equal to A inverse times B inverse. Why is that false? That looks okay to me. Yes, Brother James. Hey, Ali. Come on, let's take it off, but I'm sorry. Brother James, he's on fire, man. Pass that up, Brother James. The St. James Hotel in Selma, Alabama. You don't stick yourself too, man. I get a lawsuit, you know. That's all I need. Okay, time is. I'm going to write it down. See, it's false because this guy's supposed to be. It shouldn't be there. It's B inverse times A inverse. Remember, that was a theorem that we proved in class. You can go back and look at that as well, right? What about C? If A and B are matrices such that AB is defined, then it is true that the transpose of AB is equal to A transpose B transpose? False. Why is that? Because it's supposed to be what? Again, it's a property. This is B transpose A transpose. Make sure you go back and review those properties, okay? And with matrices, look, you just can't put a matrix over here or say, oh, well, it's still being multiplied. No, that's not true always with matrices. It's the location of the multiplication that's important, right? There's something in combinatorics, mathematics, that we call either a permutation or a combination. A combination doesn't matter about the order, but a permutation is concerned about the order. Where they're placed is important, as well as the number nomenclature. So here, the sum of two invertible matrices of the same size must be invertible. Sounds good, but it says it's false. Here's the reason why it's false. The sum of two invertible matrices, so if I have one matrix that's invertible, if I have another matrix that's invertible, if I add them up, is that sum always invertible? Not necessarily. Give a counter example. Give an example where it's false. Let me give you one right here. This is my favorite one. This follows us all the way through linear algebra. You better write it down because I'm saying something really, really big. This is 1, 0, 0, 1 plus negative 1, 0, 0, negative 1. Both of these matrices have inverses. Matter of fact, their inverses are exactly what they are. But when I add them up, I get the zero matrix. Does the zero matrix have an inverse? No, it doesn't, because I cannot produce the identity matrix from that zero matrix, right? So that's the reason why it's false. Okay, everything else is true, 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 so that's good. Let me give you this. Write this down. Where did I put it? And then we'll go, okay? Sorry to hold you over for a few minutes, but I think this is important for the test. This is test number 1. This is how it's going to look. Numbers 1 to 3. Solve the system by Gaussian or Gauss-Jordan methods. Forms. Number 4, solve the system by inspection. So just say solve by inspection, comma, find the inverse of a 2 by 2 matrix. Number 5, multiply matrices. Here I have trace and or the transpose. Just have the statement there, but here I'm saying I may ask you the question, what's the trace of this matrix? What's the transpose of this matrix? Number 6, find the inverse of a 3 by 3. Number 7, adding, subtracting matrices, equal matrices. Number 8, application problem. Something very similar to that problem where we have that parabola and you want to determine the values of a, little a, b, and c. Might not be as difficult as that problem. My goal, my philosophy in class is that I try to teach up here and I grade and I test below that. Okay, so it won't be as difficult as that, but if you can do that one, understand that problem, you have no problem with the problem that I have on the test. Number 9, true and false. Number 10, what you all been waiting for, you got to prove something, right? That's fine. Well, that's it. Thank you.